Hello and welcome to the 13th in this lecture series on understanding science. Today's topic is a very important one in science, and it's one that I've largely dodged so far, but the time has finally come. After so many lectures when I've talked about how extraordinary claims require extraordinary evidence, and I've given ideas for how extraordinary evidence should be of such quality that it overcomes a very low Bayesian prior, what I haven't actually said is how exactly we should measure the quality of evidence. What is it about a study that tells us that it's a significant result, rather than just consistent with chance? How do bias and error interfere with our efforts to understand the significance of our results? How can individual researchers influence their outcomes, either consciously or unconsciously, in order to make their results seem even more important than they actually are? All this and more will be covered in today's lecture, and if you haven't already realised it, this lecture will build to some degree on topics that we've already covered, especially the lecture on Bayes theory and some others. I highly suggest you watch these lectures in order because that's how I planned them. Anyway, let's get started. Sometimes I wonder how different my life would be if instead of learning about science, I'd instead learned how to do magic tricks to impress people at parties. Magic and science are, although you may never have thought about it, actually very closely linked, because one of the most important things that we must answer as a sceptical scientist is, how might we be wrong? When we design an experiment, we need to understand the many ways in which human beings can consciously trick other human beings, or even more interestingly, can unconsciously trick themselves into believing things that aren't real. When we watch a magic trick, we see exactly that phenomenon in action. We know that the guy with the saw isn't really cutting the woman in half, but everything our senses tell us suggests that he is. In other words, stage magic is a wonderful example of why a science-based approach is much more than just an evidence-based approach. Science uses not just the immediately available evidence, but also a large body of accumulated knowledge, called the laws of nature. An evidence-based approach would consider only the new evidence, and ignore the Bayesian prior. Anyone acting merely on evidence should conclude that the magician has sawn the lady in half. A scientist knows that this cannot possibly be true. Magic also shows us something very interesting about the human mind, that we're terrible at appreciating probability and randomness. A fine example of that is the concept of cold reading, popularised by stage mediums and psychics, but used for all of human history, as far as I can tell, to convince people that you know things that you could not possibly know. One of the tricks of cold reading is to put out a number of guesses based on the best available probabilistic reasoning you can muster, and hope that some of it turns out to be accurate. It relies on the fact that people are not very good at appreciating how predictable some facts of life are. For example, the famous mathematical fact that says that when there are just 23 people in a room, the chances are roughly 50-50 that 2 people in that room will share the same birthday. Yet in such a situation, most people would incorrectly find it remarkable if such a coincidence occurred. Statistics also tell us why, when British magician Derren Brown flicked heads 10 times in a row using an unbiased coin, he wasn't using psychic powers at all. The topic of significance aims to tease out truly important results from merely statistical anomalies. It tells us when we've discovered something exceptional and when we've just had a lucky coincidence. And often those can look very similar, which is why we need dispassionate statistical analysis to tell us which is which. The most important concept that you need to understand when considering significance is the idea that randomness can be surprisingly lumpy. By that, what I mean is that random effects sometimes cause outcomes that seem very non-random. Here's a good example. I want you to think of a random 4-digit PIN, the kind of thing that you might use for a credit card. Now, if you thought of one at random, most people will pick 4 different digits. Whereas, as it happens, almost exactly half of the possible 4-digit pins involve at least one repeated digit. But when you ask human beings to come up with a random sequence, they're much less likely than they should be to include repeated digits. For some reason, repeated digits look non-random, because randomness is all about chaos and repetition seems like order. Studies show that random sequences generated by human beings actually have very significant non-random components. They look random to us because they don't have as much identifiable form, but in fact randomness is clumpy, as I said. Here's an example of 100 randomly generated digits, and I swear this was the first one I generated, and I didn't specifically look for sequences with lots of repetitions or anything like that. So, as you look through that sequence, you notice a few things. There are very few significant clumps in this sequence, but there are a few. Near the middle there is a sequence 88388, where 4 of the 5 digits are the same. Then near the end there is a sequence 141441414141, which looks spectacularly non-random. To a vague approximation, there's only a chance of about 1 in 24,000 of a run of the same 2 digits for 11 consecutive places in a sequence of 100 random digits, so that's fun. It's also got a 5 on either side. The entire sequence starts with a 9 and ends with 2 of them, and there are 3 9s in a row about a third of the way through, surrounded on either side by a 2. So the sequences generated by computers are generally not quite random and do have some non-random artifacts in them. But in general, such sequences are pretty close to fully random, and I generated these from code on my computer which was initialized with the specific clock time when I ran it. I wouldn't ever get the same sequence again, and if I'd chosen to run the program even a millisecond later, I would have obtained a different sequence. If I did hit a specific aspect of non-random behavior in the number generator, then even that was random chance. Hopefully you understand what I've been saying now. Random numbers do not necessarily look very random to the human eye. And that's important because it also means that random events don't necessarily look random either. In fact, that's the effect behind almost every single honest pseudoscientific claim. I don't include deliberate con tricks here, but those people who have genuinely been convinced that some pseudoscientific claim is true have usually done so because they saw results that looked really significant, but were in fact insignificant and random. It's very difficult to overstate how important this is. In fact, let's talk next about one of the phenomena where this effect is most clearly demonstrated. Probably one of the most obvious manifestations of a misunderstanding of significance is in the world of superstition. We all know some superstitious sayings and actions, and it's pretty much certain that we've all done superstitious things at points in our lives. Some of us probably still do. Yet the single most important and revealing fact about superstitions is that they're different in every culture. In most Western cultures, for example, the number 13 is allegedly unlucky, whereas in China and Japan it's the number 4, and for totally different reasons. Yet the number 8 is lucky in those same countries. Why? Well, purely for historical reasons and linguistic reasons. There is, of course, no evidence to show that certain numbers are more lucky or unlucky than others. There's also no evidence that breaking a mirror brings you 7 years of bad luck, or that a chimney sweep will bring you good luck at your wedding. Yet people rely on superstitions for all aspects of their lives, from relationships to childbirth to health and success. There are many reasons for superstitions, of course, and it's an incredibly complicated subject, but one of the main reasons is confirmation bias, and that's an extremely common form of incorrectly judging the significance of events. We've met this before, but just as a recap, confirmation bias is what happens when you pay more attention to data that confirm your pre-existing hypothesis than data that disprove it. So if you believe that a certain person is a nice person, for example, you might pay more attention to their charity works, and you're more likely to remember those things, but you might skip right over the times when that person was rude or arrogant. And vice versa. If you already thought that they were not a pleasant person, you'd pay more attention to, and you'd preferentially remember, the bad things they did. If you're out looking for evidence to prove a theory you have, then you're going to get confirmation bias. What you should do, as a good scientist, is to look for information that tells you whether the theory is true or not, and not prejudice the data in one direction or the other. With superstitions, I think it's obvious where this is leading. For example, some of you will have noticed that this presentation is number 13, and that immediately primed you to notice things that went wrong, maybe. On Friday the 13th, which is considered an unlucky day in Western cultures, you're way more likely to notice and remember an unfortunate event than you would be on any other day. So as soon as a certain day is believed to be lucky or unlucky, that belief will reinforce itself. So how does superstition fit in with our theme of significance? Well, we're actually very nearly there. Confirmation bias is an example of getting significance wrong, and we get it wrong because we only pay attention to a part of the data available to us. Namely, we pay attention to the bits that confirm our superstition and ignore the bits that don't. If nothing goes wrong on Friday the 13th, then we won't remember that at all. And if something goes wrong on, say, Tuesday the 26th, then nobody ever thinks about linking it to the date. Think about it like this. If I was a fan of a particular football team and I wanted to convince you that they were great, and I only ever showed you matches that they won, then you'd be perfectly sensible if you concluded that my team was the greatest ever. I achieved a false level of significance by omitting a large quantity of the available data. Notice I didn't lie here, I didn't make up any data, I just omitted some of the data, and that was enough. This is exactly how superstition works. If you believe that your purple socks are lucky, then you'll notice lucky things that happen when you wear them. But you won't notice unlucky things that happen when you wear them. And you won't notice lucky things that happen when you don't wear them. In your mind, there is just a long string of lucky things that happened when wearing your purple socks. So they become your lucky socks, and a superstition is born. Soon it becomes a psychological issue. If you don't have your lucky socks on, then you feel less lucky. And studies show that luck is largely about attitude. People who feel lucky tend to take more chances, and they tend to be more sociable, so they tend to get more lucky breaks because they're simply manufacturing more chances to get lucky breaks. And vice versa. People who feel less lucky take fewer chances and simply don't put themselves in the positions where good things could happen to them. And so the lucky socks really do start having a genuine effect. But of course, it's not the socks at all, it's you. There are, of course, many other fascinating aspects to superstitions, such as how we tend to overweight the chance and the severity of bad things that might happen to us. So we're willing to go through a bit more pain than is rational to avoid those bad things. And if that means never getting in a car whenever it's Friday the 13th, then that's a small price to pay. And of course, our beliefs are reinforced by the culture in which we find ourselves, so the development of superstitions is amplified by the beliefs of others. We feel peer pressure to conform with the beliefs of society around us. Perhaps only slightly, but it's definitely there. So if everyone else thinks a certain thing is unlucky, we tend to agree. Right, let's move on and start looking at significance in more detail. What does it really mean? When a scientist reports that a finding they've made is significant, they mean something very specific by that claim. Statistical significance is all about working out how unlikely a particular result would have been given a null hypothesis. That is, if the claim being investigated were not true, how likely would it be to get such a result purely by accident? Let me give you an example. Let's go back to flipping coins. If I give you a coin and tell you it's biased, how would you test that? Let's say I tell you it's biased heavily towards heads. You flip it and it turns up heads. Does that confirm my claim? Well, no, of course not. Even a perfectly fair coin would turn up heads half the time. So say we flip again and we get another heads. Now is the coin biased? Well, we've got 2 heads from 2 flips. There's a 1 in 4 chance of getting this result. If you think about it, there are 4 possible outcomes. Heads heads, heads tails, tails heads, and tails tails. Only one of those, i.e. 1 in 4, is heads heads. So a 1 in 4 chance, or 25%, means that if we got a perfectly fair coin and flipped it twice, then 1 time in 4 we would expect to get 2 heads anyway, on a perfectly unbiased coin. So although the evidence we've gathered is definitely in agreement with the predictions made by the biased coin hypothesis, it's definitely not significant enough to conclude that the hypothesis is true. Perhaps more interestingly, if I said a coin were biased towards heads, you flipped it once and it showed tails, does that mean it's definitely not biased towards heads? Well, no, not at all, but it is definitely another piece of evidence pointing against that conclusion. So how many times do you think you need to flip a coin and get heads before you are reasonably confident to label the coin as biased? 3, 4, 10, 100? The idea behind statistical significance is that we can set benchmarks based on how unlikely a certain outcome would be in normal circumstances. So getting heads heads on a fair coin is a 25% likely outcome. If we flipped a coin twice and got heads heads, then we have some evidence that it might be biased, but it's really not that significant because 1 out of 4 times we would expect that purely by chance from an unbiased coin. Let's say we look at throwing the coin 5 times. We get heads on all 5 throws. Well, the chance of that happening is 1 in 32, or just over 3%. Now that sounds to me like a fairly significant result. That's the kind of thing I'd expect from a biased coin. Now let's note that this isn't absolute proof. There's still a 3% chance of getting this kind of result with a perfectly fair coin, but it's at least a fairly weighty piece of evidence now. Scientists use mathematical methods to model processes like these, and these models give us a natural measure for significance, the standard deviation. You may remember that from high school maths classes. If you pick a large number of random samples from a population, in this case we're performing many trials of flipping a coin a number of times, the standard deviation tells us how much, on average, you would expect each new trial to deviate from the mean result. The exact mathematical description doesn't matter too much, but to illustrate the sort of thing I mean, think about the heights of human adults. In the UK, for example, the average adult male is approximately 175 centimetres in height. But if we take a random sample of 10 adult males from the UK population, none of them will be precisely 175 centimetres high. They'll cover a range of heights. I don't know what the standard deviation of heights would be, but I guess it's maybe 10 centimetres. The higher that number, the more you would expect individual members of your sample to deviate from the average height. If that value were exactly 0, then that would mean that all adult men in the UK were precisely the same height. So the standard deviation tells us how variable a certain population is. And remember, that population could literally be a population of individuals like adult males in the UK, or it could be a set of samples of some value, like flipping a coin 5 times and measuring the number of heads. Though there are many ways to measure significance, one very important measure involves the standard deviation, and it provides a very convenient shorthand for this topic of significance. It so happens that a very large number of natural processes obey something called a normal distribution. I guess the clue's in the name there. It's also sometimes known as a bell-shaped distribution or a Gaussian distribution, after the first person to describe it mathematically, the German mathematician Johann Carl Friedrich Gauss, who described it in a paper of 1809. In fact, because of the way the maths works out, it turns out that repeatedly measuring pretty much anything gives you results that obey this distribution to varying degrees of accuracy. The normal distribution is very precisely defined, but in practice, what it says is that this property, whatever you're measuring, such as heights of randomly selected adult males, has an average value, and it has some spread around that average value which depends on the standard deviation, and it's probably roughly symmetric to either side too. That is to say, a man is just as likely to be 5 centimetres under the average as 5 centimetres above the average height. In the mathematical description of the normal distribution, the standard deviation parameter is usually given by the Greek letter sigma. Hence, sigma becomes shorthand for standard deviation. And remember, the larger sigma the standard deviation is, the less uniform the population you're sampling is. The smaller sigma is, the more uniform the population. So given the mathematical definition of this distribution, and the proof, which you can look up if you care, that pretty much all sampling exercises end up with normally distributed numbers, you can actually calculate what fraction of samples should lie within 1 sigma, or 1 standard deviation, of the average value. It turns out that this value is just over 68%. So that means that for anything you measure which obeys a normal distribution, which, as I've said, is really pretty much everything, slightly less than 32% of samples are outside this range of plus or minus 1 sigma from the mean. For 2 sigma, or 2 standard deviations away from the mean, this number increases to 95%, with just under 5% lying outside the range. And the probability of getting a value within plus or minus 3 sigma of the average is 99.7%. These 3 benchmark values, 1, 2, 3 sigma at 68%, 95% and 99.7%, are very handy shorthand for various levels of significance that you might want to display in a scientific paper. A 1 sigma result is not really very significant at all. A 2 sigma result is quite significant, and in many branches of science this is considered enough to publish, at least as an interesting preliminary finding. A 3 sigma result is very significant, with only a 3 in 1,000 chance of getting such a result by chance alone. In particle physics, the general threshold is 5 sigma, which corresponds to a chance of 1 in 3.5 million of obtaining that kind of result merely by chance. So when the scientists at the Large Hadron Collider announced the discovery of the Higgs boson in 2012, what they really meant was that they'd obtained a 5 sigma result. So either they'd genuinely seen a particle with the properties expected of the Higgs boson, or otherwise they gathered data that purely by chance gave a result that was so unusual that such a result would only happen once in every 3.5 million times. When a scientist conducts a study to investigate some claim, what they're really looking for is a significant result. But as we've seen, significance is just a measure of how unlikely the result would have been under a null hypothesis, that is, assuming that the claim was actually false. If I'm testing a new medical treatment, what I'm really looking for is a result that shows that my treatment is significantly better than not treating a patient, or it's significantly better than the previous best treatment. If I get a 2 sigma result, as we've learned, then that just means that the results were sufficiently unusual that I would only expect them 5% of the time if my new treatment were no better than the baseline that I'm comparing against. Of course, the corollary of that means that 5% of the time, even when studying a completely worthless treatment, I'm still going to get a 2 sigma result. This realization has some very serious implications. Most importantly, it shows how a dishonest researcher could produce impressively positive results for a certain completely useless treatment. All they need to do is run 20 studies and publish the best one, the top 5%. The other 19 could be quietly forgotten about and ignored. Strictly speaking, that researcher hasn't lied or fabricated any results. They haven't been directly fraudulent. All they've done is only given a part of the story. And though this is something that a malicious person or organisation could do, I reckon that's very rarely the case, but it is certainly something that could happen entirely by accident. It's quite possible that 20 different laboratories might have the same idea and begin researching it separately without even knowing that the others are doing so. Then the 19 who don't get anything interesting don't bother publishing, or maybe they try to publish but they're refused publication because their result isn't of interest. But the one laboratory who does find positive results, purely by fluke, will go ahead and publish. And nobody has been dishonest or manipulative here, nobody's tried to mislead, but still the scientific literature ends up with a false finding, a positive result for a treatment that actually doesn't work. This is known as publication bias, and it's a huge problem. Related to this is the concept of researcher degrees of freedom. This is actually the same problem, but on a different level. In this case, a researcher is interested in the effects of a new drug, say, that they're working on. Perhaps it's designed to lower blood pressure. So they give it to 100 volunteers and measure their blood pressure, plus a wide range of other measurements just to make sure that the drug doesn't have any other unexpected side effects. They run the trial, they gather the data, and they do their analysis, and lo and behold, the drug has no statistically significant effect on blood pressure at all. But then they notice something strange. Of those other measurements they took, they noticed that there is a statistically significant reduction in, say, LDL cholesterol across a sample of volunteers. Excited, they immediately published their findings, announcing that they might have found a new drug to help with cholesterol reduction. Perhaps you see what's wrong with that conclusion. It's exactly the same as with publication bias. The experimenters here have essentially measured a range of variables, say 20 of them, and unsurprisingly, one of them gave a statistically significant, i.e. a 1 in 20 or 2 sigma, result. This is just what we'd expect by random chance. The researchers, not being trained in statistics, don't realise this and go ahead and publish anyway. Once more, they haven't done anything immoral, they haven't lied or withheld information, and they haven't tried to deceive anyone. But their actions have resulted in a potentially false conclusion becoming part of the scientific literature. Doctors might see that study and consider giving this new medication to their patients off-label. Lives could be lost. There are other aspects to the researcher degrees of freedom problem. For a start, it's easy to play the old gambler's trick of quitting while you're ahead. If a researcher is measuring a continually changing variable, say we look at blood pressure again, then this is likely to vary a fair amount day to day just by random fluctuations, levels of stress or exercise, and a number of other factors. Let's say a volunteer starts taking a certain drug and the researcher monitors their blood pressure for 1 year. Then, after just 4 months, the patient's blood pressure appears to have dropped significantly. The researcher stops the study at that point and publishes the results. Do you see what's happened again? The researcher has given themselves another way of multiplying their chances of a positive result. Perhaps the patient's blood pressure was genuinely improving because of the drug, but perhaps it was just natural fluctuation. If the study had continued for the full year, maybe the blood pressure would have gone back up again, or maybe not. But the researcher has artificially stopped the experiment early, as soon as they got the result that they wanted. It's just like the gambler who goes to Las Vegas, makes a few easy dollars on blackjack, and decides that they have the magic touch. If they stop there, they'll end up ahead, but they never do, of course. They go back in and hope that their luck will continue, and almost inevitably it never does, and they lose all of their previous winnings. Knowing what's true and what's false is really important, but perhaps nowhere does it have a more obvious effect than in medicine. The combined issues that I've touched on this slide are so dangerous that we must find a way to deal with them. And of course that's exactly what has been done, and the solution is extremely cheap and surprisingly simple. You force all researchers who are performing studies on any medicine to register their studies before they're carried out, and to publish them whatever the result. Also, force them to register the techniques they will employ, the outcomes that they're measuring, and their criteria for statistical significance. It's so simple, but it neatly solves all of these problems. For a start, researchers can no longer carry out a study, get a null result, and just throw it away. Now they have to register that they're doing the study, and they're forced to publish those results, whatever they might be. So in the case above, when 20 studies were done but only one was positive and only that one was published, now we know that, and we aren't forced to make a conclusion based on a small subset of the data, but we get to look at all the data and make a more accurate decision. And in the second case, where the researcher was able to choose the outcomes that gave the most remarkable results, well, that's no longer possible either. In that study, they would have to measure just the main variable that they were looking at, blood pressure in that example, and their published paper would have to address just that one single variable and conclude that the result was not significant. And they would also be forced to measure it for exactly the length of time that they put in their pre-registered experiment protocol, so they couldn't stop early when they got a good result. It solves all of the problems, and indeed the scientific community is looking to do exactly this across a wide range of disciplines. I think we're almost there. We understand what significance is all about. We know that it has a fairly subtle meaning which ties in with the chance that a particular result might just be a fluke and not a new and interesting effect. And now we know, at least for a subset of experimental studies, primarily in medicine and psychology, how we can vastly reduce the problems caused by researcher degrees of freedom by forcing all studies to be pre-registered. But there's one more trick up our sleeve, and it's one of the greatest strengths of science. Specifically that science does not dictate truths, but it deals in a continually updating measure of confidence. It positions claims on the spectrum of certainty, and is always shuffling them around towards one end or the other. And the way it does that is by continued repetition and replication. Let's say we performed a study and got a 2 sigma result. That means, if you recall, that the result had only a 5% chance of happening by chance if our hypothesized effect were false. What's happening here? Well, we've come up with an idea, perhaps some kind of effect, and we want to test if it's true. This might be the claim that our new drug reduces blood pressure, or it might be the claim that the Higgs boson is real. So we're comparing two possibilities. Either the effect we're testing is true, or it's false. We design a study that will measure some value that helps us to distinguish between these two possibilities. So if we get a 2 sigma result, what that really means is that the results are what we would expect if our claim is true, but if our claim was false, we would only expect such a result roughly 1 time in 20. So it's a balance of probabilities. How could we improve that result? Well, there are many ways, of course. We might be able to tighten up the experiment to make sure that we look for a 3 sigma result instead of a 2 sigma result. That's sometimes possible, but it's not always easy. For a start, the effect might be really small, so getting from 2 sigma to 3 sigma might be incredibly difficult. Moreover, it's possible that the reason why we got a 2 sigma result was because our experiment had some fundamental flaw. There is another way. What if another team attempted to copy our experiment? There are 2 ways this could happen. Either they could look at the description of our experiment that we wrote in our paper when we were publishing the experiment, and they set up something identical and see if they get the same results. Or else they could start from scratch and try to come up with a completely different way of testing the same claim. If they tried the former idea, then that would be a good start. They could set up our experiment and replicate the exact same results, and that would give us a much greater confidence in the results that we got. It would be much less likely, for example, that our result was caused by faulty equipment or incorrect calibration of our instruments, or something like that. And repeating a 1 in 20 result gives us a 1 in 400 result. Because of the way the maths works, 2 sigma results don't give a 4 sigma result, unfortunately, but they do produce something a little better than 3 sigma, which is great. If you think about it, what we've done here is create a situation where a false positive result is even less likely. Now, either the 2 studies have got the exact result we expect if our claim is true, or, if our claim's false, then not just 1 but now 2 different experiments have got an unlikely 2 sigma result entirely by chance. And the likelihood of that happening is much lower than when we just had 1 experiment, so effectively that makes the result even more significant. But we still have the option that the whole design of our experiment is wrong for some reason, so replicating it exactly is just repeating the same mistakes. Here's where the second idea comes in. If another unrelated team can find a different way of testing the same claim, and they also get a good, significant result, then that gives us vastly more confidence in the conclusion. Not only does it give us a much higher significance, but it also helps to remove the potential cause for concern that the positive results might just have been caused by a flaw with our experimental design. For example, if we were testing a drug to reduce blood pressure, and we gave it to 100 people and then isolated them in a laboratory where they had carefully prepared healthy meals and plenty of exercise for the duration of the experiment, then we might not be too surprised if their blood pressure changed significantly. If we replicated the experiment, then we would probably get similar results, even if it was a different laboratory with different volunteers, and it would be significant. That's to say, we could tell that the blood pressure had definitely dropped by a significant amount. The problem with the experiment design was that we changed too many variables at once, so concluding that the new drug had caused the effect would probably be a false conclusion. The effect was significant, but it might not have been caused by the drug. It might just have been caused by the lifestyle changes that we imposed on our volunteers. However, if a different clinic carried out another test on the drug, this time controlling for diet and lifestyle properly, and perhaps measuring the outcomes differently, but they still saw a significant drop, then that would give us a lot more confidence in our conclusion. Well, that's the end of this lecture on significance. I hope it cleared up a few things for you. Let's go through what we learned and the important things to take away from this. Firstly, significance is all about random chance and testing hypotheses. A result is significant if it seems to favour our hypothesis more than the alternative, and the degree of significance depends on how much it favours our hypothesis over the others. In particular, we tend to look at how likely it would be to get a result if our hypothesis were true or false. A highly significant result in favour of our hypothesis is one that's highly likely to occur if our hypothesis is true, but highly unlikely to occur if it's false. We measure this likelihood by many methods, but today I've introduced the concept of standard deviations, often known in mathematical shorthand as sigma. When you're taking samples from a population of individuals or taking repeated measurements of a certain property, results often cluster around a mean or average value, and they often do so symmetrically, with a characteristic spread which is this standard deviation. The smaller the standard deviation, the more tightly the results cluster around the mean. In lots of cases, just because of the way the maths works out, values tend to fall into a so-called normal distribution. In this case, we can say something specifically about the fraction of all samples that we would expect to fall within plus or minus 1 sigma, or 2 sigma, or 3 sigma of the mean. In fact, we expect to see 68%, 95%, and 99.7% of samples within those ranges respectively. This gives us a convenient shorthand for significance in scientific papers, where a 2 sigma result refers to a result that is at least 2 standard deviations away from the mean. The chance of such a result happening randomly is therefore roughly 5%, or 1 in 20. There are lots of ways we can get false significance, in particular by failing to declare all the measurements that we made, either by not publishing negative studies or by not describing all aspects of the studies we carried out, when perhaps only a minority of measurements might actually have showed anything abnormal. Fortunately, we can get round this by ensuring that studies are pre-registered ahead of time, and then are published regardless of their results. We can also avoid getting misleading results by ensuring that other teams can copy our studies and encouraging them to do so, perhaps using slightly different methodology to avoid experimental error. That's the end of this lecture. I hope you found it useful. If you enjoy these lectures and you think you know other people who might benefit from learning more about science, then please spread the word and get them out to as many people as possible. I'm hoping to release another one in a few weeks' time, so do subscribe to get the latest notifications. And if you have any suggestions for new videos, please let me know. For now, however, next time will be the final lecture in this new series. I'll be talking about skepticism itself. I'll be giving you the full pitch for scientific skepticism as a guiding principle in human society. What is skepticism? Why is it important? And how can we use it to improve the world we live in? Thanks very much for your time.